Hello everyone, my name is Mohammad Shapun and I'm here to present our work Residual Connection-Based Graph Convolutional Neural Networks for Gait Recognition. This work is supervised by Professor Marina Gavrilova from Biometric Technologies Laboratory, University of Calgary. All the portraits and contacts of the authors are available in this slide. The following is a small overview of the presentation. First, an introduction to gait recognition will be given, and along with that, we will discuss about the motivation of this work. Afterwards, we'll discuss the prior works that was done on gait recognition. After that, we'll discuss the contributions of our work. The methodology and experimental analysis with previous methods will follow. Lastly, we'll conclude our presentation by summarizing our work and talking about the future works. First, let's talk about gait recognition. Gait recognition refers to identifying a person by their walking pattern. Person identification is an emerging topic as it is related to prevent fraudulent activities. Several different types of biometric traits are used for identifying a person, such as face, palm, iris, gait, etc. However, among all the biometric traits, gait can be considered as the most useful due to its several uniqueness. Gait recognition has several applications in the field of cybersecurity, computer graphics, activity recognition, and many other problems. But why gait recognition gained so much popularity? The gait pattern of all individuals are completely unique, and there are some unique features of gait information in terms of person identification. The gait pattern can be captured from a very long distance, and only a camera is sufficient to capture gait information. In addition, it can be performed without any assistance of humans, and also it can be performed in low resolution, which makes it easier to perform biometric recognition. Currently, there are several methods exist for gait recognition. However, these methods suffer in terms of accuracy when it comes to variety of viewing angles and different accessories carrying condition. Therefore, the purpose of our work is to propose a solution which is view and accessories invariant. In this slide, we'll take a look at some of the previous works that took place on gait recognition. Wu et al. Proposed convolutional neural network with handcrafted histogram features and used them to fine-tune the CNN network. Zhang et al. Proposed an autoencoder and long short-term memory network to extract discriminative and spatiotemporal features, and later they used these features for classification. Wolf et al. Proposed a direct classification method using 3D CNN, where they pass the gait sequence directly into a 3D CNN and later classifies them. These are the methods that are directly implemented using deep learning techniques. Now let's take a look at some of the work that used skeletal features. Li et al. Used pose estimation method to extract 18 2D coordinates and then transform them into a spatiotemporal features into a discriminative features for classification. Shaikh et al. Used open pose estimation method to extract handcrafted features. And based on the joint coordinates, a 64-dimensional embedding vector was generated, and later this embedding vector was used to train a deep learning model. Liao et al. Proposed pose-based temporal spatial network, and this proposed method was particularly able to handle different accessories carrying conditions. Finally, He et al. Proposed a multitask generative adversarial networks for gait recognition. This paper has made the following contributions. A novel graph convolutional neural network-based architecture was proposed. This method utilizes the dynamic modality of the skeleton sequences to achieve high resistance to low-quality data and varied walking conditions. Residual connections are incorporated with GCNN for improving the performance. Furthermore, global attention sum pooling layer is used after the GCNN layer for faster convergence and to get rid of unnecessary information. Finally, we used CASIA-B Dataset for evaluating the performance of our proposed method. This figure illustrates the framework of the proposed method. First, the input videos are passed into a pose estimation network to extract body joint coordinates. And later, based on the body joint coordinates, we have extracted the gait cycles. And later, from these gait cycles, we have transformed them into a graph representation. Later, this graph represented data is passed into our proposed RGCNN architecture for final classification. Pose estimation is a method for estimating pose of a person from a given image or video. This method extracts body joint coordinates of a person from an image or video. There are several existing methods available for pose estimation, and some of the mentionable are open pose, PoseNet, and dense pose. Based on the previous performance and the performance of different pose estimation methods, open pose architecture was used in this work. Now let's take a look about the gait cycles. Gait cycle represent the information of a gait sequence when one foot hits on the ground and again it comes contact with the ground. One single gait sequence contains sufficient information to distinguish individuals. Based on the previous research work, in this work double support phase-based method was used for gait cycle extraction. After extracting the data from the pose estimation architecture and by calculating the gait cycles, the skeleton data is later transformed into a graph form. Here, the joints are represented as vertices and bones are represented as edges. The graph consists of two different subsets. The first subset is an intraskeleton subset, which represents the edges that are inside a skeleton, and the other one represents the interframe edges, which represents the edges that are in between different frames. Graph convolutional neural network is a new branch of neural networks. Graphs naturally arise in many real-world applications, including social analysis, fraud detection, traffic prediction, computer vision, and many more. By representing the data as a graph, the structural information can be encoded to model the relationship among entities and furnish more promising, insightful underlying the data. Traditional convolutional neural networks are capable of handling vector and matrix represented data. However, when it comes to graph representation data, traditional convolutional neural networks fail. This is where graph convolutional neural network comes. The idea behind graph convolutional neural network is for each node, we compute the feature information for all its neighboring nodes and of course the feature of itself. So let's assume we use an average function and we do it for all the nodes. And finally, this result we put into a neural network for final classification. So this method is actually called neighborhood data aggregation, where we collect information from all the neighborhood nodes and puts it together to get the final information. Global attention sum pooling layer is incorporated to transform the output of the GCNN into one dimension. The pooling layer uses a sum operation to pool sets of features, leaving smaller and distinctive number of features. This helps to reduce overfitting and faster convergence. This equation denotes the global attention sum pooling layer operation. This is the architecture of the proposed GCNN. First, we pass two inputs into the GCNN architecture. The one is the feature vector and another one is the adjacency matrix of the graph. Then it passes through a graph convolutional neural network with residual connection architecture, and then we perform batch normalization on them. And we repeat this same stack of layers one more time until it goes into a global attention sum pooling layer. Finally, after flattening this whole two-dimensional input, we pass it into a fully connected layer for our final classification. Now let's take a look at the CASIA-B dataset. As the primary purpose of our work was to show that our proposed method is view and accessories invariant, the CASIA-B dataset was a perfect dataset for us. This dataset contains 124 subjects videos in 3 different walking conditions, and all these data were collected from 11 different viewing angles. The walking conditions are normal, back carrying condition, and float carrying condition. The total number of videos in this dataset are 13,640. Now let's take a look how we have set up the dataset for training and testing. So the first 74 subjects video data were used only for training purpose. We have trained our architecture with those 74 subjects data. The rest of the 50 subjects data were only used for testing purpose. We have used a gallery probe based testing mechanism. So in the gallery, All the first 4 normal walking condition videos of the 50 subjects were put into the gallery set, and the rest of the sequences were put into the probe set. From our architecture, we have generated an intermediary embedding vector, and later we passed our gallery data and probe data into our architecture to get the corresponding embedding vector. And later we have used cosine similarity distance measurement to compute the distance between the gallery and the probe data. Whichever gallery data produce the minimum distance is considered to be the class of that probe data. In our experiments, we have used root mean square propagation optimizer to optimize the gradients during backpropagation. We have experimented with categorical cross entropy and triplet loss function. Triplet loss function is denoted as the following equation. So in triplet loss function, we have 3 types of data. One is anchor data, one is positive data, and one is negative data. The anchor and the positive data belongs to the same class, whereas the negative data belongs to any other class. The objective of this function is to reduce the distance between the anchor and the positive data and increase the distance between the anchor and the negative data. To show the superiority of our proposed method, we have performed 3 different experiments. First, we trained our model with original GCNN. Secondly, we experimented by incorporating the residual connection into the GCNN. And in the final experiment, we have incorporated both the residual connection and global attention sum pooling layer into the GCNN. Table 2 demonstrates the accuracy that we have achieved for all the experiments, and it shows that for experiment 3 and our proposed method, we have achieved highest accuracy. This table represents the rank 1 accuracy of our proposed method with the previous state-of-the-art methods. The reason behind choosing these 6 different methods is that they have all used CASIA-B datasets, and they all have partitioned the dataset exactly in the same manner that we have. We can see that our proposed method with RMSProp optimizer and triplet loss achieved higher accuracy than all the previous methods and for all the working conditions. In addition to that, for all the different viewing angles, our proposed method also outperforms the previous methods. We have compared our work with categorical cross entropy loss function, and we can see that using the triplet loss function produces much higher accuracy than categorical cross entropy. These figures illustrate a bar graph for showing the performance of the proposed method with the previous method. We can see that for back carrying and cloth carrying condition, our proposed method gained significant higher accuracy in terms of accuracy. We have generated our cumulative matching characteristics for rank 10 accuracy. This curve depicts the increment of the performance as the rank of the accuracy measure increases. We can clearly see that as the rank increases, the performance of our proposed method also increases. Finally, we have reached at the end of our presentation. In this work, a novel residual connection-based GCNN method was proposed. This method aggregates the feature map from one frame to another by utilizing the body joint relationships to enhance the accuracy. This proposed method shows performance improvement not only for normal walking condition, but also for other walking conditions that are available on the dataset. Now, in terms of our future work, we will study other architectures to extract more discriminative feature maps. In addition, we will also investigate the performance of this method without retaining the hierarchical feature map on low quality videos. These are the references that we have used in this presentation. Thank you very much everyone for listening to our presentation. Now we'll be taking questions. Please feel free to ask any questions if you have any confusions.